In this video, we're going to do some practice problems relating to optimization and applications of optimization. So our first example says, from a 6 by 6 inch piece of cardboard, square corners are cut out of the sides so that the sides can be folded up to create a box with no top. What dimensions would maximize the volume of the box? So we're going to do our step-by-step process. Step 1, we're going to draw a picture. We have a 6 by 6 inch piece of cardboard. So 6 inches on the side, 6 inches on the side. And we are going to cut corners out of, cut squares out of the corners. So that I can take shape that we are left with and fold the four sides to get a box with no top. So it's an empty box. All right, so try to draw a picture. Let's try to assign variables, try to understand what's going on. What's going to change from where we cut is going to be the size of that X right there. That's what's going to change from problem to problem. But note that it has to be the same for all of these. We have X all the way around. So that's what our variable is going to be, is the X is the size of the corner that we cut out. Just say the side, not the size, side of the corner cut out. All right, step 2. What are we trying to maximize or minimize here? We are trying to maximize volume, which is going to be equal to length times width times height. Length, width, height. So let's think about, with our picture, what are length, width, and height? Well, here the height is going to be the height of one of these sides that we fold up, which is going to be the length of the square that we have. So h here is just going to be equal to x. The width, which we'll call this guy right here, is going to be the width right there, which is this length in our picture. And note that that is going to be 6 minus 2x. And also note that's going to be the same as the length as well. The length is going to be the same as these right here, and that's going to be also 6 minus 2x. The whole side is 6. We take out 2 x's, and we get 6 minus 2x. So overall, we have the volume is length 6 minus 2x, width 6 minus 2x, height x. Put it all together. It was good to FOIL this. We get 36 minus 24x plus 4x squared, all times x. So overall, 36x minus 24x squared plus 4x cubed. So this is a weird problem because step 3 and 4 are not needed. There's not two variables that we have here, just the one variable x, and we already have our function of x. So step 5, let's think about the domain. So what is the largest value x can be, and what is the smallest value x can be? Well, the largest value x can be is, or sorry, smallest can be is 0. This is kind of what we did before. 0 would give us a very dumb box. In fact, it would just be flat. Right, this is a box with no height. But we just know that the volume is 0 in that case. And the largest value x could be is where 6 minus 2 times x is equal to 0, or when x is equal to 3. We cut out 3 from each side. And again, we're going to have the volume be 0 in that case, as we're not going to have length or width. So our domain here is going to be 0 to 3. And just like we did in the previous video, we're going to include 0 and 3 so that we can use the nice theorem that we have. All right, step 6, we need to find the global max of our function on the interval 0 to 3. So we're going to find the derivative. That's 36 minus 48x plus 12x squared. We're going to set that derivative equal to 0. We can factor out a 12, and we're left with 3 minus 4x plus x squared. Write that as 12 and x minus 3, x minus 1. So we get 3 and 1 here as critical points. The derivative doesn't exist at x equals 0 and 3, the endpoints. So now we just have to plug in those points, 0, 1, and 3. We know when we plug in 0 and 3, we get 0. That's the volume, and we kind of already said that's going to be 0 when we have that. We can double check it, but that's going to be the case. When we plug in 1, we get 36 minus 24 plus 4. That's 12 plus 4 is going to be 16. And that's going to be our global max. So put it all together. Step 7. What dimensions would maximize the volume? The dimensions of the box would be when x is equal to 1. That means that the height is equal to 1, and the length and the width, 1 inch, and the length and the width should be equal to 6 minus 2 times 1, or 4 inches each. So this is a 1 by 4 by 4 inch box. So we can see in our picture, we have the picture of our function. We have at 1, we got 16 as our volume. At 0 and 3, our volume was 0. And then the volume actually keeps on going past that, but we only cared about from 0 to 3. It didn't really make sense to have our function past 3. All right, let's do a much different problem. A bus company charges $10 per person for a sightseeing trip if 30 people travel in a group. If the company reduces the charge by 20 cents for each person above 30 in the group, how many people will maximize the total revenue for the bus company? So this is an example where we can't really draw a picture, but we can assign our variable. X is going to be the number of people above 30 in the group. Now, you could define it in a different way. You could define it as the number of people in the group, and it just includes the 30, but I think it's going to be easier to set up if we have it greater than 30. And as long as you're consistent with how you assign your variables, there's multiple ways you can go about it. All right, so we're saying that this bus company is going to make the money for 30 people regardless. We're just trying to figure out how many more people could be in the group to maximize the amount of money they bring in. They decrease the cost every time a new person joins. So when does it kind of, the new person not outweigh the cost that comes down? At some point, if it keeps on bringing the cost down, it's not going to make any sense to bring in a new person, as you'll lose money by keeping, you'll like literally give them money to decrease the cost. So you need to kind of figure out when's that going to be. So step 2, note that we are trying to maximize. That means find the global maximum of revenue, which is how much money we are bringing in. So the revenue here is going to be the cost of the ticket, $10, times the number of people who are riding, 30. So regardless of what happens, we're going to make 10 times $30. But then we are also going to have each person above 30 that comes in. So here the cost of the ticket is going to be 10 minus 0.2x. And how many people does that refer to? X people. So this is the cost of the ticket. This is the cost of the ticket. And this is the number of people. Number of people. And we need two kind of parts here. The $300 that we make no matter what, and then plus the extra people. And note that we don't need step 3 and 4, just like in the previous problem, in this example, because we already have just one variable, so we don't need another one. So our function here is given there, and we need to find the domain. So the domain, what is the largest value x can be? What is the smallest value x can be? Well, we know the smallest value x could be is 0. We could have no more than, or we could have only 30 people show up. Even if there's 20 people that show up, you still get, we know we're going to maximize revenue if we have 30 show up, so we don't want anything less than that. We can kind of build that into the formula, but I think it's fine like that. The largest value x could be in the context of the problem would be when 10 minus 0.2x is equal to 0. At that point now, the cost doesn't really make any sense, as it's going to be negative or 0 at that point. And this is going to be when x is equal to 50. So our domain, even though it won't make sense for 0 or for 50, we're going to have our closed and bracket domain, but those are going to be able for us to do our extreme value theorem kind of thing here. So step 6, we are going to find the global max of f of x equals 300 plus 10x minus 0.2x squared. That's our function where I've distributed everything out on the domain 0 to 50. Again, if it's less than 0, let's say X is equal, or we have 20 people show up in the group. We're not maximizing our revenue. We want 30 people in the group at least. So 0 is our smallest. 50, we start now having negative cost, and that's definitely not going to work. So 0 to 50 is something that makes sense here. That's good. To find the global max, we need to find the critical points. So we find the derivative, which is going to be 10 minus 0.4x. We set that equal to 0. 10 equals 0.4x, so x is going to be equal to 25. And the derivative does not exist at 0 and 50, the endpoints. So plugging everything into the function, we have f of 0 is going to give us something, f of 25 is going to give us something, f of 50 is going to give us something. F of 0 is going to give us just the 300 that we always have. Same with f of 50. And f of 25 is going to be our answer. It's going to be 300 plus 10 minus 0.2 times 25 times 25. And this is going to be equal to $425. Step 7, let's just put it back in terms of the problem. How many people will maximize the total revenue for the bus company? We should have x equals 25, so that is 25 more than 30. We should have 55 people total, or 25 more than 30. And the revenue would be 425 when it's maximized. All right, let's do a much different problem than that. A flexible tube of length 6 meters is bent into an L shape. Where should the bend be made to minimize the distance between the two ends? So step 1 now, a picture is really important here. So we have some kind of flexible tube. And we're going to bend into an L. And we are going to look at the distance. We'll call that D, the distance between those 2 points. So what we want to find is where to make that bend. So maybe we should call our 2 sides X and Y. Let's do some examples and maybe some, what's not happening. If we have the bend made nowhere, so that's like X is equal to 0, Y is equal to 0, the distance is just going to be 6 meters, right? We could make it maybe at X is equal to 1 and Y is equal to 5. And we just need to figure out what the distance is and see if it's the minimum distance that we have. The distance when X is equal to 0, Y equal to 0 would just be 6. And it's going to get smaller if we kind of bring it in. So let's need to find what are the values of X and Y that work there. All right, step 2. We're trying to minimize distance. So I need to find the distance formula, D, which is going to be the square root. It's going to be like the Pythagorean theorem. This is equal to the square root of x squared plus y squared. X squared plus y squared equals d squared. Take the square root. All right, we have 2 variables, so now we need to do the step 3 and 4 business. Our constraint equation is going to be the fact that we have 6 meters total. That is that x plus y has to be equal to 6. We did an example with 1 and 5. We could do 3 and 3, 0 and 6, but it has to be equal to 6. So step 4, use the constraint equation to write our function in terms of one variable. We could write this as y equals 6 minus x and plug this into the distance formula. So d is equal to square root of x squared minus 6 minus x squared. Now there's one little note here before we can write down our function. You could do this with the square root, but note that d is minimized when d squared is minimized. And that's just a fancy way of saying that we're just going to consider, so we don't have to deal with the square root, we're just going to consider f of x equals x squared plus 6 minus x squared. This is equal to d squared. We don't really care what the distance is, even though we could just take the square root of whatever we get. We care about where should it be made, and it's going to be the same whether we deal with a square or not a square. You are not going to be expected to do anything like this on your own. This is just something for this specific problem that we could do to make the work easier to do. All right, step 5, let's look at the domain. Think about what is the smallest value x can be. In this case, that's going to be 0. And what's the largest value x can be? In this case, that's going to be 6. To find the largest value, you could just ask what's the smallest value y could be and get the same thing. Our domain is going to be nice and easy, 0 to 6 here. So putting everything together, step 6, we're going to find the global min of our function x squared plus 6 minus x squared on the interval 0 to 6. So let's find our derivative. That's going to be 2x plus chain rule 2 times 6 minus x times the derivative of 6 minus x, which is going to give us 2x minus 2 times 6 minus x. That is 2x minus 12 plus 2x, or 4x minus 12. Set this equal to 0, we get x is equal to 3, which may not be very surprising if you thought about this problem kind of beforehand. When does the derivative not exist? At 0 and 6. So that's going to be critical points. Plug everything into the function, f of 0, f of 3, f of 6. F of 0 is going to give us 0, not 0. F of 0 is going to give us 6. 6 squared. F of 6 is going to give us 6 squared. And f of 3 is going to give us something less than that. 3 squared plus 6 minus 3 squared, which is going to be 9 plus 9, or 18 instead of 36. Note that the actual distance here is going to be the square root of 18, but it works the same. Step 7, put it in terms of the problem. Where should the bent be made in the 6-meter tube? The bent should be made in the middle to minimize distance. We should have x equal to 3 and y equal to 3. All right, let's do one more problem. Different problem than that. We have a piece of wire of length 20 centimeters is cut into 2 pieces. One piece is made into a circle and the rest is made into a square. Find the amount of wire that should be used for the circle, or equivalently the square, to maximize area, or said differently, where should you cut the original wire to maximize area? So step one, let's draw a picture. We have 20 centimeters of wire. And we are going to take some scissors and we're going to cut that wire at some point, and we're going to use part of that wire just for a square, and the rest is going to be made into a circle. So we're going to try to find where should I make this cut that I maximize the area of the square and the circle put together. So there's different ways to do it, but I think maybe the nicest way to do this is to call x the distance on the left and y the distance on the right. And note that you could even do it at the very beginning. Maybe you know this is going to be y equals 20 minus x. That's kind of doing step 3 at the same time. We'll do it explicitly when we get to that point. All right, step 2. We are trying to maximize the area of the circle and square. So let's think about this. The circle, or the square, let's start with that, is going to be x, the perimeter is equal to x. So each side is going to be 1/4 x. So the area of the square is going to be 1/4 x squared. When we think about the circle, we have the perimeter, or the circumference, is equal to y, which means that we have 2 pi r is equal to y. So r is equal to y over 2 pi. So the area of the circle should be pi r squared, pi y over 2 pi squared. And we're going to add those together, and that is our function that we're trying to maximize. Note that another way you could do this is you could call your two variables the radius of the circle and the side of the square. And that might be a nicer way in terms of calculation, but the picture is going to be a little bit more messy at the beginning. There's positives and negatives to a lot of different ways of going about this. Also, the step 3 would be more complicated if you did it that way. But here we know that x plus y has to equal 20. We only have 20 centimeters total. When we cut it, we have x and y. So we have maybe y is equal to 20 minus x. Step 4, let's put everything in terms of one variable. We have y equals 20 minus x, so our function that we're trying to maximize is going to be pi 20 minus x over 2 pi squared plus 1/4 x squared. And let's simplify this function now. We have pi over 20 minus x squared over 2 pi squared plus 1/16 x squared. We have a pi here. Actually, we can keep it a little bit further. 2 pi squared is 4 pi squared. We have a pi in the numerator, pi in the denominator. We have 20 minus x squared is 400 minus 40x plus x squared over 4 pi plus 1/16 x squared. Maybe it's nice to combine that into one fraction. We can write this as 400 minus 40x plus x squared times 4 plus pi x squared all over 16 pi. And we'll come up here, finish that. That's going to be 1600 minus 160x plus 4x squared plus pi x squared all over 16 pi. Maybe it's best to write that as 1 over 16 pi, 1600 minus 160x plus 4 plus pi x squared. All right, now let's think about step 5. What's the smallest value x can be? In this case, that's going to be 0. And what's the largest value x can be? That's going to be 20. So 0 to 20 is my domain. If you made your variables r and the side length for the square, the domain would be more complicated instead of the function being more complicated. At some point, you're going to have to deal with that complication. It's really up to you which way you want to go about it. All right, on the next page, let's rewrite the function in the domain. So we have find the global max of this kind of gross looking function on the interval 0 to 20. Even though this is a gross looking function, the derivative is fairly easy to find as it's just a polynomial. It's going to be 1 over 16 pi that comes along for the ride, negative 160x plus 2 times 4 plus pi x. We're going to set that equal to 0 and note that the derivative doesn't exist at the endpoints, 0 and 20. All right, when we set this equal to 0, this constant's going to go away, and we're going to be left with negative 160x plus 8x plus, actually, we're just going to leave it as, plus 8 plus 2 pi x. This is, not 160x, just 160. As the derivative of 160x is 160. Set this equal to 0. We get 8 plus 2 pi x equals 160. 160 over 8 plus 2 pi, which is about 11.2 or so. All right, so now let's plug in our 3 points. F of 0, f of about 11.2, 160 over 8 plus 2 pi, and f of 20. When we plug in 0, we're going to get 1600 over 16 pi. That is 100 divided by pi, which is about 31.8. When I plug in 20, I'm going to get, which will give 25. And that's actually not surprising because that's just the area of a square with length 5 everywhere. The area for 0 would be the area of a circle. That's why it's a decimal form there. And finally, if I plug in my special point about 11.2, I get, should be about 14. So actually, the special point we found was the global min. And our answer is going to be one of the endpoints, having everything be the circle. So the question asks, if we go back to the question, where should you cut the original wire to maximize area? Step 7, all the wires should be used for the circle. To maximize area. That is, we should have x equals 0. So in all these problems, they're all very, very different. The steps that we use are all the same. The difficulty is just seeing in the problem, what's the function, what's the picture I need to draw, what's the domain, and then we kind of do the same thing past steps 6 and 7. This is a difficult section for many students. The only way you can kind of get better is to jump into practice problems, ask questions if you have it, and just really dive into it. Best of luck, and let me know if you have questions.